Hi, everybody. Welcome to the webinar, and thank you so much for being here and joining us on our fourth installment of our AMP Up Your Devices webinar series. In this series, we are showing examples of how our Fusion AX system can be used to study nanoelectronic devices in situ electron microscopy. My name is Nienke Kans, and I'm an application specialist here working at Prototypes. And today I'm joined by a very special speaker who is a talented speaker who is going to discuss a very interesting topic. And the topic is going to be probing atomic migration in PMTJ breakdown through in situ analytical STEM. I'll go ahead and introduce Dr. Hwanhui, who is here with us today. And I'll tell you a little bit about her background and about what she's doing now. So Dr. Yun earned her bachelor's degree in chemical engineering at Hanyang University in Seoul, Korea, and her PhD degrees in chemical engineering at the University of Minnesota in the USA. She is a recipient of prestigious Fulbright GE scholarship for her undergraduate studies and the Samsung Scholarship for a doctoral degree. During her PhD, Dr. Yun made notable contributions to the study of various atomic structures in perovskite oxides, employing analytical STEM. Her research included the discovery of unique metallic line defects in barium tin oxides and the study of dislocations in barium tin oxides as well, and two-dimensional black arsenic. Following her PhD, Hwanhui continued her research as a postdoctoral fellow at the University of Minnesota, and there she broadened her research scope to include in situ TEM. Her postdoctoral work involved the use of advanced in situ TEM techniques to study the phase transformation mechanisms of platinum tin alloys and breakdown behaviors of PMTJ devices, which is the topic of today. She also investigated perovskite-related oxide materials via ab initio calculations, adopting the group's theoretical approach. At this moment, Dr. Yun is a senior researcher at Korea Research Institute of Chemical Technology, or KRICT, in South Korea. At KRICT, her current research focuses on understanding crystal phase and local atomic structures in perovskite halides by utilizing analytic STEM, and continuing her trajectory contributions to the field of TEM-based material science. So if you're ready, Dr. Hwanhui, I'm going to shut down my camera and my sound, and then you can just start your presentation. Thank you so much.
All right. Thank you for the introduction. And can you hear me, by the way?
Yes, we hear you loud and clear. Everything's working fine. Perfect.
Can you see my screen as well?
Yes, that is working fine as well. Thank you for checking.
All right, great. Thank you very much. All right, thank you, Nienke, for introducing myself. And hello, everyone. My name is Hwanhui, and I'm currently at the Korea Research Institute of Chemical Technology in Daejeon in Korea. Firstly, I'd like to begin by thanking the Prototypes people who invited me to this Prototype seminar and all of you for attending my talk today. By the way, I've just returned to my work after maternity leave, and also it's midnight in Korea, so please excuse me if I'm a bit rusty in this talk. I will be discussing my research on proving atomic migration in PMTJ breakdown through in situ analytical STEM. This study was conducted while I was studying at the University of Minnesota, and here we exploited these powerful in situ biasing TEM techniques, which were provided by Prototypes. And also we combined this in situ TEM with the analytical STEM, including STEM EDX and STEM ILS. So this study explores the dynamic behaviors and properties of these PMTJ junctions at the nanoscale, which are crucial for advancing magnetic storage technology. So let me begin my talk. First, what is an MTJ, or magnetic tunnel junction? An MTJ magnetic tunnel junction is a key component in spintronic memory devices. In conventional normal electronic memory devices, data is stored by charging a small capacitor representing a 0 or 1 H However, as the demand for faster and more energy-efficient memory increases, new field, spintronics, is gaining attention to shed light on these storage, memory device fields. So what is spintronics? Spintronics is a field that uses the electron's spin, which is an inherent property of the electron. And in the spintronics, the spin is used for data storage and transfer. Unlike traditional method, it relies on the spin states of the electrons, not the charge or electron transport in the material. So something like this. In the spintronics, the MTJ, magnetic tunnel junction, is the key or basic component. And the structure of the MTJ is like this. MTJ consists of two ferromagnetic layers separated by an insulating barrier. So there are three layers as a core structure. And then by controlling the spin orientation of these ferromagnetic layers, data can be stored as 0 or 1. Here, between these two ferromagnetic layers, one is a reference layer and the other is a free layer. This reference layer has a fixed spin orientation, and regardless of any conditions, the reference layer's spin orientation doesn't change. On the other hand, the other free layer has a variable spin orientations. So by configuring the spin orientations of these free layers, we can store the data as 0 or 1. If the free layer has an anti-parallel orientation to the reference layer, then it becomes this AP anti-parallel, and then it can store the data as 0. And then if it has the orientation parallel to the reference layer, then it becomes 1. Then, so to make these 1 and 0 layers, people have been making, researchers have been making a lot of new designs using various materials and structures. Here, in our work, our research focuses on the perpendicular magnetic tunnel junction, PMTJ, where the spin direction is perpendicular to the MTJ's neck, as illustrated in this presentation. The spin configuration of these MTJ units can be controlled by many external forces, such as electric fields or magnetic fields. And in our work, we examine the current-induced switching in PMTJ devices. So these configurations result in different tunneling resistance. When we have a parallel configuration between the reference and free layers, it generates lower resistance. And when we have an anti-parallel configuration, the MTJ device will show higher resistance. So if we plot the IV curve or resistance current curve, the graph becomes like this. So first, when current flows from free layer to reference layer, the MTJ step becomes parallel. And then, as I said, parallel configuration has the lower current, which is this resistance I curve. And when the current flows in the opposite direction, then the configuration becomes anti-parallel and it becomes 0. So in the RI, resistance current graph, the resistance shows the higher resistance as shown here. So this is the common graph in these MTJ devices. And this is the basic kind of mechanism in the MTJ device. And to make more scalable PMTJ units and then make it more useful, these MTJ devices are designed in this nanopillar structure. And this nanopillar structure is fabricated between the top electrode and bottom electrode. However, when researchers make these nanopillar structured PMTJ devices, they show significant instability issues. And these instability issues with device failures stem from fabrication processes or operational conditions. My colleague found that the success rate is less than 20%. In addition, the current flowing through this MTJ unit can impact the stability of the MTJ units, so the current becomes also a problem in the instability. So to address these issues and to improve the stability of these MTJ devices, we employed the in-situ TM, and then we also employed the analytical STEM to investigate the mechanisms behind failure in PMTJ devices. So first, let's discuss our device structures. In the top-down view image, the top and bottom electrodes are patterned to sandwich the main MTJ nanopillar. So here, as shown in this image, top electrodes are crossing in the lateral direction, and then the bottom electrodes are crossing in the vertical direction, like in this image. And then the MTJ stack is deposited between these top and bottom electrodes. And then this is the top-down view SEM image showing the small, like 50 nanometer diameter nanopillar device. In the cross-sectional view, the electrodes consist of this bottom tantalum, ruthenium, tantalum bottom electrode, and then the top electrode consists of ruthenium and tantalum. And then between these top and bottom electrodes, there are these main MTJ units, which are cobalt iron boron and magnesium oxide, which are the ferromagnetic layer and the insulating barrier layer. And also we included this molybdenum, and this is included to enhance spin polarization within the MTJ. So this design optimizes the magnetic and electrical properties of the MTJ device, making the improved performance in this device. So our collaborators fabricated the PMTJ sample, and then we looked it in the TM. And using this, we first carried out the basic structural characterization using STEM. Here, I'm showing the HDF STEM image of the device. As shown, as expected, there are bottom tantalum, ruthenium, titanium bottom electrode, and there is this top electrode. And like above the tantalum and ruthenium, we used titanium and gold as a top electrode. And then there is this nanopillar structure, and then outside there is this silicon oxide, which are just capping the nanopillar structure. If we check the EDX maps, we can clearly see that all of the layers are grown well as we designed and desired. We can see that in the EDX map, there are main magnesium oxide barrier layer and also cobalt iron boron ferromagnetic layers. And then there are molybdenum and then tantalum as shown here. And so we kind of carefully checked the structural integrity of these PMTJ devices. First, you can see that, so this is the region, the main core MTJ unit region. Here we can see that in the HDF STEM image, it's not clear, but if we check the bright field STEM image, we can see that there are lattice contrast because of this crystallinity in the magnesium oxide and cobalt iron boron. It shows that the main layers have the uniform thicknesses, And also the interfaces are very smooth. And then all of the layers shows the lattice contrast, showing that their crystallinity is relatively good. So next, after checking the structure of these PMTJ devices, we started doing the TM experiments. So for that, we have to make the in-situ TM sample. FIB was used to make the in-situ TM sample. This is an example image. This is an SEM image obtained while during the FIB sample preparation. And then this is the TM image of the in-situ sample. In-situ sample. And then actually I will explain more about the details of the sample preparation. But after making this in-situ TM sample, we found that similar this IV curve or resistance current curve is made, showing that like successfully the proper in-situ TM sample was made. So here the TM in-situ sample preparation procedure is kind of summarized. So I will go over this procedure because this is in-situ TM related seminar, and also this is the key and the most important part in the in-situ experiments. First, we have to find and identify and position the fabric, the region of interest. We check the like a SEM image, and then we kind of locate the center nanopillar. Because nanopillar is very small, like we should be very careful, and then we should be careful not to kind of coat on the like sample too much, because it will become like unidentifiable. And then next, we cut like one side of the bottom electrode, and that is because we want to make the current flowing in the vertical direction in the nanopillar. So by cutting this one side in this side view, we are kind of making the current flowing from this like left side direction in the bottom electrode, and then cross the nanopillar, and then flow in the top electrode. And then third, we fill the cut region using the carbon to make it insulating. And then next, we deposited this platinum so that it makes the electric current path to connect the top electrode to the TM biasing chip. And then next, we kind of deposited a carbon protection layer so that like there is no any other current path that is made around this structure. And then for the FIB processing, and then to reduce any FIB damage, we added one more platinum protection layer as shown here. And then after this, we are all ready. And so we kind of we make the lamella in this sample. Then we take this lamellar structure out from this on-chip like substrate. And then next, we will have, we kind of polish the structure, polish the lamella so that it is electron transparent for the TM imaging and TM experiments. And this is the like almost done sample. And then lastly, we have to cut the top platinum electrode so that the current doesn't flow from like the top layer. So in this design, the current will like the biasing chip will be connected to the left and right side, and then like from the left side, the yellow this bottom electrode is connected to the nanopillar, and then in the right side, because there is this carbon deposition which is cutting the bottom electrode only the top electrode will and platinum will be connected to the right side, so that the current will flow in the vertical direction, the nanopillar core region. So by using this design, like we apply the bias, we apply the electric field, and then this is our exemplary like image after each biasing. So this is showing, like, this is the hot stamp image of the MTJ device. And then as we apply the current, like the structure shows some changes. It's not clear, and then I will talk more and more details later. But this shows that the structural change shows that proper electric path is made, and then the in-situ biasing experiments are carried out properly. So here we need to decide what kind of imaging mode we use. And in this case, here like we use the bright field stem image. Commonly, what we use is hot stem image, but in this case, we have this magnesium oxide and magnesium oxide, which is very which is made of very light elements, and there are this tantalum, which is heavy metals. So because of these high G atomic number differences, the hot stem images doesn't show the crystallinity clearly. So we cannot see the lattice contrast well. So to overcome this issue, we adopted this bright field stem image. In bright field stem images, we can clearly see the contrast from the lattice, so that and we can see the structural change better. This is also seen in this line profile obtained across the core region. You can see that although we cannot see the lattice fringe in this hot stem image, in the bright field stem images, we can see this lattice fringes better. So first, we decided to use the bright field stem images, and then next, it is important to see the identical locations in this image in these experiments. In the case of this PMTJ device, the nanopillars is around 50 nanometer diameter, and also because we are making these TM samples, and because of the focal depth is just a few nanometer, when we just image one layer, we might be seeing the surface of the TM images or inside the TM images. I think I'm not explaining it well, but to make the experiments more rigid, we did the focal series. We acquired the focal series for each data, and then we find the same depth in each data set, so that we can compare the each data set, and we can track the structural changes better. So for example, in one sample, we got the first initially we got the focal series with the step size of 4 nanometer as shown here, and then after applying the bias at 500 microampere, we also obtained the focal series with the 4 nanometer step as shown here. And then by comparing these two focal series, we found that there are the center region, and then we only use this central region to publish any data and we examine the structural changes. And then next, what is important is to check the electron degradation. In this case, we worried that the a long irradiation of the electron beam will deteriorate the structure, and then will just change any results. So we checked whether the beam degradation happens during these experiments. First, there are two cases when the long irradiation happens. One is when we acquire focal series because we are requiring like many images, there are many like because then electron beam will be radiated a lot. So there is a chance that the specimen will be degraded. In this case, before and after focal series acquisition, we can see that there is no clear like a beam degradation at all. And the second case, the specimen can be degraded, is the EDX acquisition. During the EDX acquisition, like we acquire the data for like 30 minutes to like a 30 minutes or like 40 minutes. So this long like acquisition time can degrade the specimen's integrity. So like we acquired these images before and after EDX acquisition, and then we found that there is no structural change. So we confirmed that the beam degradation is not the like any source of the like fault data or any wrong data. So after checking these focal series and beam degradation effect, we started our experiments. In this experiment, we applied this triangular wave current as a current input. This bias stress cycle is applied. Then we measure the resistance during the cycle, and also we also monitor the device structure using TM imaging. Here we found that at each cycle, to see the current effect on the structures, at each cycle we gradually increase the maximum current to examine the current effect and then see the changes because of the maximum current. Actually, more than 30 devices were fabricated, and among them, 10 devices exhibited just proper device structures without any structural failure. And here is our results. So first, the initial bias stress cycle showed that the resistance is inversely proportional to the stem sample thickness. The stem sample thickness was measured using the is-log ratio method. And this inversely proportional relationship evidences that proper current flow through the PMTJ nanopillars was achieved. And then next, we applied the successive bias cycles with increasing maximum current, and we observed that there is a gradual resistance decrease as shown here. So after we apply the current, there is a change in the resistance. And then to the reason for this decrease in the resistance, we monitor the Bright-Field stem image. And this is the Bright-Field stem image before biasing any current, before biasing. Here, after biasing with the maximum current of 100 microampere and 500 microampere, we can see that the structure is changing gradually. Here are like notable structure changes shown with these arrows. Specifically, this magnesium oxide layer becomes more non-uniform, and then the cobalt iron boron and magnesium oxide interface becomes rougher. Here we found that there is locally thin regions in this magnesium oxide layer. And these like locally thin regions are referred to as pinholes. And we also obtained the EDX maps from this pinhole, and we found that there are definitely less magnesium, and then there are more iron and cobalt in this region. These pinholes can induce leakage current, and these pinhole formation during like this breakdown have been speculated in many previous studies and literatures, but there have been no like any direct evidence about these pinholes. But our work provides the first direct visualization of this phenomena, so which is very meaningful. So we were very glad to see that this pinhole was captured. So like this first very gradual change, a small change in the IV electrical properties of this PMTJ is the soft breakdown in the PMTJ device. In addition to this, the pinhole formation, significant degradation occurs near the edge regions of the nanopillar devices. As seen in this video, the application of the current causes noticeable changes in the shape of these edge regions. In detail, the tantalum tail region diffuses further, and then it creates the connection between the top and bottom electrode. And this diffusion results in the increased leakage current and the reduction of the resistance. Ninke, by the way, I think my PowerPoint stopped. So
Oh, is it stuck? Okay, let us see.
I think
is it stuck from your side, or is it just stuck?
Yeah, I think it's just my PC.
We can give it
one. Sorry
one.
about it.
That's okay. That's okay. Let's see. Let's
give
it 1 second. Yeah, let's give it 1 second. Maybe I can ask one question in the meantime while it's trying to get
sure.
get back up again. We have one coming, which is actually
I'll try to just reopen the file.
Of course. Well, are you okay doing a multitasking while you're reopening the file, and I'll see if I can ask you a question that came in. Let me see. So we have one question that says she was wondering about the electrical behavior of the carbon protective layers deposited during the FIB preparation. So are they not electrically conductive, and how does that influence your measurements, if that makes sense, while the PowerPoint is starting up again?
Can you repeat the question again?
Yeah, of course,
which
of course.
less properties of the.
Sorry, the sound is breaking up now a little bit as well on my side, at least.
It was connecting, so I couldn't.
Yeah. Let's try this again. Yeah. So the question was, they were wondering about the electrical behavior of the carbon protective layers deposited during the preparation. Are they also not electrically conductive, and does that change any of your electrical behavior if there's carbon on top, if that makes sense?
Yeah.
Oh, now the sound is cutting out, at least from my side.
Yeah, so carbon layers are insulating in this case. So we designed it so that it doesn't affect the electric behavior of the PMTJ device.
Okay, I think the sound is cutting out. Let's see if we can get you back completely. Let's first see if we can get the presentation up, and maybe if you turn off your camera and see if that works with the sound a little bit better. I can see that the presentation has stopped now, which is great. That's awesome. Let's see if we can get the presentation back up.
I think that's a good idea.
Yeah.
Yeah.
Awesome.
So are you seeing my screen now, by the way, without the presentation, but with just my desktop?
Exactly, and I can see the presentation starting up as well again.
Yeah.
Awesome.
All right.
So you were saying that the carbon protective layer is there, but it is not really, is it being cut through basically when you're doing the cut in the fib preparation, if that makes sense?
Yeah, like the, you mean the, were you talking about the carbon protection layer on top?
Yes, yes.
Top of
yes.
the device, by the way?
Yes, exactly.
Yeah, that layer is, I thought that like you were talking about the carbon deposition on the bottom in the cut layer. And like basically we expected it to be insulated.
I understand. Yeah, she doesn't really say if it's top or bottom, but that's clear. Hey, I can see a presentation, I think, again. Yeah, I can see it now with the the presenter slide, but that's okay.
Right?
Yeah, it works. Awesome.
All right, great. I'm so sorry.
It's okay. This happens. Don't worry.
I think like we can start from
from here. This is where you were
here, maybe.
video. Yes, perfect. I'll shut down my sound again, and thank you guys for having some patience as well. We'll continue from here.
I'm so sorry about this issue, and I will continue my talk here. So yeah, as I said before, in addition to the formation of the pinholes, like significant degradation happens near the edge region in the nanopillar. So as illustrated in this image, like it shows the tantalum region diffuses further, and then it creates the connection between the top and bottom layer. And I think the same kind of like my PowerPoint is frozen again with the same.
Yeah, I can see it. You can see it. It is the same. It's the same slide. It doesn't want to anymore. It just doesn't like that slide.
Because of the video in this slide.
Yeah, it just doesn't like it.
This is a disaster.
It happens, don't worry. I can ask you another question while it's restarting, and maybe then we can try and see if we can just skip that one slide and just go from there.
Yeah, I think that's a better idea.
Yeah, exactly. I'll just ask you one more question while it's going, because then we can use this time to answer some questions that came in. So somebody's asking, at what electron energy have the experiments been made? Radiation bombardment may graphitize carbon layers and increase its effect on the experiment or not. This may also explain some reduction of electrical resistance.
So first of all, like about the electric energy that was used here is all based on our collaborators. So like the current density was identical to the experimental, actually like when I showed the IV curve, I showed that there is a parallel configuration and then anti-parallel configuration where the high resistance and then low resistance is made. And then so like it is important to kind of see the change between the high resistance and the low resistances. And that change happens at the switching current. And then there is kind of the the current that changes. And then so like that means we gotta increase the current up to that point, so that we can kind of make the anti-parallel and then parallel configurations. So we kind of noticed that there is the critical current, but we started from very low current, because there should be some changes in the low current as well. So actually, as shown in the current slide, we started from very small current, small maximum current biasing, and we slowly increased the maximum current to the critical current. And actually the the smallest current was just decided based on the prototype's in-situ order like specification. Like this was a reliably acquired data, and that's how we used. So did I answer it properly?
Yeah, I think so. I think that was a great answer. Awesome.
And then the next was about yeah.
Oh yeah, the next part indeed was about the radiation bombardment and the graphitization of the carbon layer. Yeah, yeah.
So the thing is, that's like why we did the like electron beam degradation experiments. Like we kind of acquired, like we examined the like structure before and after the long like electron beam irradiation, like during the EDX mapping or like during the like focal series acquisition. And then there was no like a like structural changes. So we just and that shows that like there is no like degradation or like this this structural changes or bombardment. That's how I. By the way, I think like I think I misunderstood the question.
I think it's okay because it's more indeed about let me see. Yeah, radiation bombardment, but I would I would think, you know, that's the same, or at least that's working similar or simultaneously with the electron bombardment, right, from the electron beam itself.
Yeah. Right. So yeah, basically like what we saw was that the structure doesn't change first, and then when we checked the like the IV curve from these experiments, their trend was kind of consistent regardless of the electron beam radiation. And then I think that kind of proves that there wasn't big changes because of the electron bombardment or any like damages, I think.
Clear. Thank you so much. Let's see if we can get the presentation up from the slide where we were at and see if it it wants to pick up from there, and then we can continue from there. Thank you for asking the questions, guys, as well, and thank you again for your patience as well with slides getting there. Yeah. Oh.
All right. I'll just go to the next page from where we left.
Yeah, I now see just your screen, the background, but no presentation yet. I think it might be either on a different screen. Yeah, there we go. And now we see it in presentation mode. Yeah. I think it's working now. Yeah, perfect. Yeah. Awesome.
I'm sweating a lot.
Don't worry. It happens. Really, don't worry.
Please edit the video before you upload it, if you can.
I think it works fine now. So let's see from here. Let's take it from here.
Okay. So next, we carried out the experiments more to understand the effect during the biasing. So for this, we applied the constant current. So before, like we were applying this triangular shape current, but now we are applying a constant current, and then we are acquiring the stem images during the biasing, and like we are also acquiring like more spectroscopy during biasing. So like on the screen, there is this ADF stem image showing the main MTJ units during or like before biasing. Like the structure shows the top tantalum layer and then molybdenum and cobalt iron boron magnesium oxide cobalt iron boron. And before, you can see that there is like high contrast in the tantalum layers, and then there are like these distinct slopes in each cobalt iron boron and magnesium oxide layers. And then also we can see that there is a slightly brighter contrast near the interface of tantalum and molybdenum, and that is because of the strain imposed in the tantalum and molybdenum, because their lattice contrast is different. And in this structure, like we applied the constant biasing. And like first, we applied in one direction, which is kind of represented as plus. And then we also apply the constant bias in the opposite direction, which is represented as like minus in this slide or in this graph. Upon applying the constant current, two changes occur in this intensity line profile across this ADF stem image. First of all, the strain contrast that was shown between the tantalum and molybdenum disappears, and it indicates that there is a relaxation happening in this structure, like when we are applying a bias. And also in the cobalt iron boron and magnesium oxide region, the distinction between the cobalt iron boron and magnesium oxide becomes unidentifiable, resulting a flat intensity profile. As you can see before in the profile, before biasing, the slope is different in the magnesium oxide and cobalt iron boron, but like during this biasing, the intensity becomes flat. And then if I pause the biasing, the intensity profile returns to the original state. After checking this structural change, we also acquired Il's core loose edges. And then we tried to observe any atomic distributions from these core edges. Here, like we acquired core iron L and cobalt L edges, as shown here. Because these iron L edges and cobalt L edges have white lines, it is very useful for elemental quantification. And this elemental quantification revealed that there are significant modifications in the cobalt and iron distributions. Before biasing, cobalt and iron show peaks at the top and bottom cobalt iron boron layers. During biasing, these merge into a broad asymmetric peak. And like this asymmetric peak shape changes with the biasing direction. And this clearly demonstrates that the atomic interdiffusion takes place because of this biasing. And then after we stopped the biasing, we found that the atomic distribution returns back to the original a two peaks shape. These changes hinted from the Il's core loose edges show that there is a significant atomic diffusion, and that it hints the source of this, the formation of the pinhole. It shows that during the biasing there is interatomic diffusion, and then because the atoms are moving a lot, it might kind of change the structure and then form this non-uniform interfaces between the layers, and then form very thin pinhole regions. So here we could hint the origin of the soft breakdown, and then the pinhole and the edge region migrations. And then next, after investigating the soft breakdown, we applied biasing cycles repeatedly more, and then we also applied a very high current to see any further breakdowns. Here, when we applied 700 microampere cycle repeatedly, we observed that there is a sudden and abrupt change in the current, as shown in this left side image or graph. After the 44th biasing cycle, the resistance jumps significantly. And then if we see the stem images in this video, STEM image revealed notable structural changes in the nanopillar device after these 44th cycles. Specifically, the top gold electrode melts and collapses at this critical point, and also like in the low magnification images, we can see that the top electrode entirely collapses, and then they are almost entirely destructed. Because of the time constraints, I cannot show all the data, but similar structural changes were also observed in the TM like heating experiments, hinting that the heat or like joule heating is the source of these destructions. During this complete breakdown, MTJ structural changes a lot as well. If we obtain the MTJ, the EDX maps from this destructed device, we can see that the cobalt iron boron layers and magnesium oxide layers are merging into one layer. So like the structure entirely collapses, and then it renders the device non-functional or malfunctional. So we could figure these two types of breakdowns. One is soft breakdown, and the second is complete breakdown, which kind of collapses the entire structure. And then the complete breakdown is related. We also found that the complete breakdown is related to the joule heating during these biasing experiments. So to summarize, we performed this operando TEM study of nanopillar PMTJ devices, and then we identified two main breakdown mechanisms. One is soft breakdown, and the second is complete breakdown. In the case of soft breakdown, the pinhole forms at the central magnesium oxide layer, and that induces the leakage current. And then secondly, at the edge of the nanopillar region, the tantalum electrode kind of melts, and that it interconnects between the bottom and top electrode. So it also decreases the resistance as well. Secondly, in the case of the complete breakdown, it happens because of the joule heating during this biasing, and that it just melts the entire structure. This work was published in the ACS Nano, so you can check the details in this paper as well. Lastly, I'd like to acknowledge my collaborators and then funding sources which made this research possible. So thank you for your attention, and I'd be happy to take any questions.
Awesome, Dr. Yun. Thank you so much for finishing the presentation, even though the trickiness with the presentation, it was really good. There are some questions still left as well. I know we did some in between, but we have some good questions here as well. So somebody is asking, if you use a Thermo Fisher stem, they should have an ADF1 and 2 detectors, which collect the differential scattering angle signals to form HAADF and LAADF. Would that be useful to enhance the contrast of the magnesium oxide layer?
So the thing is, like in the Thermo Fisher, or like I haven't used any other like a stem, like a CSTM, except for the Thermo Fisher companies. But you know, like there are these high angle ADF stem images, and also low angle or medium angle ADF stem images, and like annular bright field stem images and bright field stem images as well. So actually, I also tried to do experiments with the low angle ADF stem images. Because first of all, like high angle ADF stem image is Z contrast, so it just relies on the atomic number. But like as I showed with the HADF stem images, because of the big atomic number differences between the tantalum and the magnesium oxide, HADF stem is not useful for this. And then secondly, low angle ADF stem images is kind of the HADF stem images plus train contrast. So it kind of has the similar issues with the HADF stem images. like when I obtained the low angle ADF-TEM images or medium angle ADF-TEM images, the distinction between the magnesium oxide layer and then tantalum layer was not clear. And also the lattice contrast was not clear in this low angle or low angle or medium angle ADF-TEM images. I think that answers the question, but plus I also acquired the annular bright field stem images and bright field stem images. And in bright field stem images, it was more visible. And then in the annular bright field stem images, I could see some like lattice contrast as well, but it was not as clear as the bright field stem images. I just used the bright field stem images. I think if I want to be more clear, or if I want to make it like more rigid, I probably would need to do some multi-slice simulations on these like two materials. But I just got the data, so and this is not the TM oriented paper, so I just kind of skipped that part. But like if you want to be more detailed, then I think it's a good idea to do some multi-slice simulations.
Yeah, I understand that. And indeed, some papers are a little bit more TEM oriented, some are a little bit more applications oriented, and this is definitely a little bit more applications oriented. Somebody else is asking, let me see, there's quite a lot of questions. So do you have any idea of the sample thickness at the analyzed region?
Oh, yeah. So the thing is, like, I got this thickness of the TM samples using the iris log ratio method. And then the thing is, I got the iris data from the silicon, like a substrate, just beneath the MTJ, like region of interest. And that is because, like, when I obtained the data, like, because, like, the region, I didn't want to kind of put too much electron beam on the like main region, and actually like because the silicon like substrate has like a better like a well-known like a mean free path, which is used in the iris log ratio method. So I thought that like using the silicon like substrate is better to kind of compute the thickness or like calculate the thickness. So that's why I used the like silicon substrate to measure the thickness. And I think there might be some changes, some differences in thicknesses between the substrate and the like a main region, but I think it shouldn't be that big. Mostly like the they were very close. Like nanopillar, the nanopillar is just above the silicon substrate. So it's just like a few hundred nanometers away from each other. So I think like if the silicon substrate is like 50 nanometer, then nanopillar should be more or less the same. It might be like a little thinner because it's like a top region, like because of the FIT process, but I think it should be more or less the same.
Yeah, that makes sense to me as well. I think that answered the question really nicely. Just due to time, there are a couple of other questions, but what we will do is we will get you in contact with the people who asked the questions, and then you can email back and forth and just see if you can answer their questions nicely. And again, yeah, thank you so much for this really insightful presentation, and thank you for all the attendees to joining this as well. Again, there will be a small survey at the end, and if you guys can fill it in.
Thank you so much for having me, by the way, but I'm so sorry about all of these like hassles.
That's absolutely fine. I mean, we got through it amazingly, and I think still the presentation was really great. So at least I thought so. And thank you again for the time, and everybody. If you want to join the next webinar, please also put in your name for that one on the website. And Dr. Hyun, thank you so much.
Perfect. All right.
Have a great evening, guys.
All right. Thank you very much. Bye.
Bye.